2, I guess. Is it correct?
No, sir.
But in the yesterday meeting, it has been told that I not understood the module 2, the problems not understood like that. Yesterday in the QCM meeting, it has been told that the problems has not understood and it's difficult to understand the module 2 like that. So can I get the response in the class usually? Okay, so I'm going to ask for each and every problem, each and every concept. I'm going to ask. So 2 to 3 times I'm going to ask. So whether you understood the concept, understood the problems, right? So I want the reply.
Yes, sir.
Yeah. So at that time you can tell if any difficulties in understanding the problem or understanding the concept. You can tell at that time, right?
Yes, sir.
So in the class, no one is going to respond. In the meeting is there with the principal sir, HOD sir. No one, even college sir, HOD senior sir is calling the names. Still, you are not able to reply for that one. Okay. Now also only you are replying, except you, no one is replying. I think you have seen your results, I guess. So what you are studying in the last semester, what the effort you have put in the last semester, that has been reflected in this semester results. Okay, semester end results you got. So my question is, okay, if you're not getting understanding the concept, so when I'm asking or when I'm doing the class, so at that time you can reply itself. So I'm not understanding this concept. Kindly repeat me once again. Or repeat me once again, twice, thrice, or you can just call me and I can ask me. I'll take the special class for you. So I'm going to repeat. Okay. So I think since the module 2 is not understood, I'm going to take the class after 4 o'clock. I'm going to take. So what the module 2 I have done so far, I'm going to take that concepts. Okay. And I'm going to do the repetition of that one. Okay. Is it okay? Is it okay for you?
Okay, sir.
Okay. So fine. Which concept you are not understood in the module 2? So others also need reply. Only one is replying that doesn't work the scenario. Okay. So others also I need the reply. So if you're not replying, it is I am going to assume that you understood the concept. So afterwards, you should not tell that the question paper was difficult. You're not able to understand the concept like that. Okay, because I am doing the things for yourself, not for myself. Okay. So if you understand the concepts, you can write very well in the exam. Okay, and you can make use of that knowledge in the in future. In the upcoming semester, I'm going to tell in the 5th semester, you're going to make use of what the concept you have studied here. You're going to make use in the 5th semester in the PCS. You're going to make use in the 6th semester digital communications. It consists of the applications of these concepts only there. Okay, in each and every concept, I think you'll be knowing. I'm going to do from the scratch till the application part I'm doing for any concept if I have taken. Do you agree with me?
Yes, sir.
So starting from the basic mathematics till the application part I am doing here. Okay, so because in order to make you people to understand in the better way where you're going to apply so that the concept can be helpful for you people, I'm doing all those things. But still, we are not replying the class and you're assuming like you're not understanding means it will not serve the purpose what I am doing in the class. If you're not understanding, kindly reply me in the class. So we are not able to understand. So you kindly repeat me. I'll give some examples so that we can understand. So that concept you can, that one you can tell so that you can understand the concepts easily, you can understand. Okay, and you can able to score good marks, and better than that one is knowledge is very important because these concepts, what are the random processes that you're going to apply in the upcoming semesters in the subjects, and moreover this random processes, so this is you're going to apply in the machine learning, which is the data science. That's a booming language, that's a booming one. So I think it'll be where you're going to apply the data science. I think you have the experience. Okay, so if you have searched in the for example, Amazon. If you have done the search in the Amazon, for example, if you shopped for one thing, so next time when you open the Amazon, it is going to suggest you, right? You might have observed that one, right? Suggestions for you, it is going to be reflected in the Amazon. Okay, so that is because of the data science here. It is okay. So you're going to assume that Google is not going to collect the data or Amazon is not going to collect your data. No, it is it is going to collect what are the activities you are doing in the web. Okay, so what are the activities you're going to do in the web? It is going to be collected. That data is going to be processed when you're going to log in again, it is going to reflect that one. Okay, suppose if you're going to enable your mobile phone with the GPS. Okay, so if it is linked with your mobile, linked with your email ID. Okay, so every month you are going to get the mail where the locations you are okay, you are visited, and all those things it is going to send in the mail that is in the timeline visited you are going to get. I guess you have seen that one. Anyone seen that one?
Yes, sir.
Yeah, that is because of everything is because of the data science. It is going to collect the data, it is going to process the data, and it is going to see that one here. So in that one, we are going to make use of applications of these concepts. Okay. So I think the problem I had done only 2 problems I had done in this model. So the problem I guess I repeated. So I'll take the class in the 4 o'clock today. Okay. So attend those who are not understand, and those who understand, everyone should attend the class. Okay. So I'll explain the problems and the concepts. Again, I'm going to explain the problems and the concept I'm going to explain. So in the last class, I given one problem as homework. So I need the answers for each and every 1 year. Okay, I'm going to call the names. I want the names. I want the answers for that one. So Manoj, Deep, can you give the answer for the covariance? I had done in the last class. I had done this problem. Manoj, Deep. Manoj, Deep, are you there? Manoj, Deep.
Yes, sir.
Yeah. So can I get the answer for this problem? This problem I given in the last class. I given the formulas also. I told what are the formulas you're supposed to use here. Okay, so everything variance is given, the mean is given. I told you how to find the answer. So can I get the answer for this one? Manoj, Deep.
Sir, last class absent, sir.
You're absent. Okay. So next one will give the answer for this one. We'll give the answer for this one.
Sir.
Yeah, tell me.
Sir, covariance of X and Y is 14.1.
14.1. Very good.
And E of XY is also 14.1, sir, because mu X and mu Y is
Yeah,
0.
very good. Very good. Very good analysis. Excellent. Yeah. Next one.
And mu U and mu V equals to 0, sir, because mean of X and Y is 0.
Yeah. Good. Very good.
And sigma U square and sigma V square, sir. Sigma U square equals to 89.96.
Yeah.
Sigma V square equals to 84.89.
84.89. Yeah. Good, Vashita. Next.
Then covariance of UV equals to 95.32.
Okay.
Rho UV equals to 1.091.
Excellent. Good analysis. Good, Vashita.
Thank you, sir.
Yeah. Okay. So done, everyone. I think everyone got the same answers. So any doubts with this problem?
No, sir.
Yeah. So what about others? What about others? So I've done the concepts. I given the explanation of everything I given. Okay. So I'm getting answer from only one. What about others? See, if you're not going to understand the concepts, you have to reply in the class itself. So each and every problem per class I'm doing. So since from the last Friday, I'm just doing the only 2 problems I did here. Okay, so 2 problems I did and 2 concepts only I explained here, not more than that one here. So if you're not able to understand, you tell me in the class. So I'm ready to explain many times till you understand. Got it? Take the next problem. See, if you observe the textbook here, in the textbook, they're not going to give the any concept. They're not going to give. Just they're going to give the formulas, and they're going to straight away they're writing the answer here. Okay, so I'm not doing like that. I'm taking the each and every concept. I'm taking still. I'm digging to the mathematics. Still basics. I'm going. Okay, from the basics. I'm scratch from the scratch. I'm explaining to you people. Right? So till the application part where you are going to use that one. Still, if you are not able to understand, means you should ask in the class. In the class, anyone asks, no one is going to reply for anything here. So without asking, without knowing whether I am God, to know your mindset, like you are understood, whether you are not understood, all those things. I'm not God. I'm just a common human being. If you're going to reply, then only I will come to know. If you're not going to reply, how do I come to know? So if you're not understood any concept at any point of time in the class, you can stop me. Okay, you can stop me at any point and you can tell me, sir, I not understood this concept. I'm going to repeat that one. Okay, so take next problem. Take the next problem. So it is a solved problem in the textbook here. So I'm going to repeat that one. So it is we are going to make use of the concept of the normalized Gaussian random variable. So that we are done in the module 1. So I'm going to recall the topic and I'm going to do this one here. So you can take the PDF of the bivariate random process. Okay, you can take like this. The bivariate PDF of the random variables x and y. Random variables x and y. The random variables x and y is given below. Is given below. Find the marginal PDFs. Find the marginal PDFs. Okay, so I'm going to write the what is the random process. Okay, so the bivariate is nothing but, so by I said it's nothing but the two random variables x and y. Okay, so that one you're going to call it as a bivariate. You are going to call here. So for that one, the PDF has been given like this. So fxy of x comma y. So I think you know this concept here. Okay, so it will be equal to the 1 divided by 1.4283 pi into exponential of minus x square minus 1.4 xy plus y square divided by 1.02. Okay, so where x and y can take the value, minus infinity is less than x comma y is less than infinity. Okay. Done. Okay, so this is the bivariate PDF it has been given here. So from this one we need to find out the marginal PDFs we need to find out here. So bivariate is nothing but it considers the two random variables. We are going to call it as a bivariate PDF here. So in the first model we are seeing for the single random variable. Okay, so now in this model the same concepts just we are extending for the multiple random variables, that is called as the two random variables we are extending here. Okay, so now what it has been asked in the question is we need to find out the marginal PDFs. Marginal PDFs is nothing but if you are going to able to obtain the single PDF of the random variable x or y, we are going to call that one as the marginal PDFs. You are going to call here marginal PDFs here. Okay, so that is called as the marginal PDFs. So you can take the marginal PDF. The marginal PDF fx of x is given by. So marginal PDF fx of x is given by. So fx of x can be obtained from this one by integrating this one with respect to the y here, because if you are going to remove the y terms, then only we can able to obtain the x terms only we can able to obtain. So that one you are going to call it as a marginal PDFs you are going to call here. So right. So in the last class also we have seen the concepts of this one here. So here integral from minus infinity plus infinity fxy of x comma y, okay, into dy we are going to integrate here. With respect to the dy we are going to integrate here, and we are going to solve this one in order to get the marginal PDFs here. So right. So in order to solve this one, I'm going to make use of the one of the concept what we studied in the module 1 here. That is for the Gaussian normalized random variable. Okay, so just I'm going to recall that concept here. So we have the normalized Gaussian random variable is there. Normalized Gaussian random variable. So we are seen in the module 1. Okay, I think you remember this one. Okay, so there is one property is there for that one here. One property is there for that one. The property is nothing but, so it is 1 divided by 2 pi. Okay, so 1 divided by 2 pi into, so just a second, yeah. So the property is 1 divided by 2 pi into integral from minus infinity to the plus infinity. Of some variable I'm going to take here, minus u square by 2 into du. So this is equal to the 1 year. Okay, 1 divided by 2 pi integral from minus infinity to plus infinity e to the power of minus u square by 2 into du is equal to the 1. So this is one of the property of the normalized Gaussian random variable. So if you are going to integrate that one, we are going to get that one. We have solved the problems on in the module 1. If you want, you can just turn the pages and you can see that one here. Okay, so now what I am going to do is, fxy of x comma yz. So here it is in the form of x square minus 1.4xy plus y square is here. So here I'm going to take some terms common. I'm going to express this one in terms of the y minus x, the whole square. I'm going to substitute for the u here, which will be in terms of the y minus x, what are the quantity you're going to get here. Then I'm going to make use of this property of the normalized Gaussian random variable. I'm going to substitute that one and we are going to get the value for the marginal PDFs you are going to get here. Okay, so understanding the concept, right? So the marginal PDFs can be obtained by integrating this one with respect to the other random variable. For example, if I want with respect to the x, I'm going to integrate with respect to the random variable y here. So since this is a example of the normalized Gaussian random variable, or it can take the form like Gaussian random variable or exponential random variable it will take here. So we are going to solve that one here. Okay, so I'm going to consider this one, whatever it is there in the exponential part I'm going to consider here. So consider we have y square minus 1.4xy, 1.4xy. Okay, so plus x square plus x square. So what I'm going to do is, so we have 1x square is there, 1x square is there. So from this one, I'm going to make it as a square. I'm going to take here. So what I'll be doing is I'm going to take some 0.7x I'm going to take here. So 0.7x I'm going to take. So you know 0.7. If you're going to take the square here, if I'm going to take the square here, so 0.7 square is nothing but it will become 0.49. It will become here. So 0.49 it will become here. So 0.49 into 1, we are going to get certain value you're going to get here. So because 1.4 is there, why I'm taking 0.7 is because we know the formula for the a plus b the whole square formula. So a minus b whole square formula. So it is nothing but a square plus b square minus 2ab. Okay, so y I'm going to consider as equal to the a here. Okay, and I'm going to consider b is equal to the something called 0.7x I'm going to take here, 0.7x here. So if I take b is equal to 0.7x, so what it will become here as per this formula, it will become y square. Okay, so plus 0.49x square. Okay, 0.49x square. So minus 2. Okay, a is nothing but it is y, and b is nothing but it is a 0.7x here, 0.7x. Okay, so this has become y square plus 0.49x square. So 2 into 0.7 will become, it is minus 1.4 into xy will get here, minus 1.4 into xy. So I can able to extract this one. That's how I taken. So I'm going to take 0.7. I'm going to take here. Okay, so if you take the 0.7, that will become 0.49x square. The remaining x square is nothing but, so 0.51x square is remaining here. Correct. So I'm going to split the one into the two parts. I'm going to split. One is called as 0.49, other one is called as a 0.51 here. So together some will become equal to the one we'll get here. Okay, are you able to getting this one right?
Yes, sir.
Yeah. So I'm going to convert this into the form like this so that I can easily express this one in terms of the y minus 0.7 the whole square plus 0.51 x square I can express here. Okay, so this quantity, what are the quantity I'm considered here? Okay, so this one I can express as a y minus 0.7 whole square plus 0.51 x square I'm going to express. How I explain the process here. Okay, so I think everyone understood. I can further, shall I go further?
Yes, sir.
Okay, so I'm going to substitute here fxy of x comma y. So this is equal to the 1 divided by, just I will rewrite this expression. Later I'm going to substitute in this part here. Okay, so 1 divided by 1.42835.
So 0.7x.
0.7
X.
yeah, x is there. Sorry, I missed here. 0.7x is there. Okay, so x is there, you note down this one. Okay, so 1.4283 pi. Okay, 83 pi. So into the remaining quantity, it's an exponential of. Okay, so I'll write as e to the power of minus. Okay, so e to the power of minus, we have, I can write this entire quantity like this here. So it is y minus 0.7x the whole square plus 0.51 x square. Okay, so whole thing divided by 1.02. Whole thing divided by 1.02. So I think you can able to see this one. Yeah, these two steps you can see. So here whole thing divided by 1.02 z. That's what I written here. Okay, now what I'm going to do is, we know the law of indices, you know, so it is e to the power of a plus b can be written as e to the power of a into e to the power of b, we can write here. So okay, so this is the law of exponential indices. Okay, so I'm going to rewrite this one. I'm going to split this part here. So 0.51 x squared divided by 1.02, I'm going to take it outside here. So it is become e to the power of 0.51 x squared. Why I'm taking outside? Because so I'm going to integrate with respect to the dy. I'm going to integrate with respect to the dy. So the x is we can treat as a constant here. So that's why from this exponential part, I'm taking this part as the outside. I'm going to take here as a constant here by applying this law of indices. Okay, so the remaining quantities, it is 0.51 x square divided by 1.02 is there, 1.02. So 0.51 x square divided by 1.02, and also minus is there. So I'm going to take e to the power of minus 0.51 x square divided by 1.02. Okay, so in the denominator we have 1.4283 pi. Okay, so the remaining quantities e to the power of minus y minus 0.7 x square divided by 1.02 will get here, 1.02. Okay, e to the power of y minus 0.7 x square divided by 1.02 you're going to get here. So this is fxy of x comma y, so which we are converted in the form of like this here. Okay, now I'm going to substitute this expression in the marginal PDF expression. I'm going to substitute here. So we are not doing any concepts with respect to the engineering statistics or the random process. This is the mathematics here. So integration already you have studied. You have studied the substitution of variables. Everything you have studied here. I'm doing just mathematics class only. I'm doing here, not the engineering statistics. Okay, these are mathematics only. Even if you consider signals, they are also mathematics only. The concept of signals will be very less will be there, right? The rest of the part is mathematics only. Okay, here also the concept of the random process or the statistics is bit only is there. So we are going to apply the mathematics for mathematical integration parts, and we are going to evaluate that one here. That's it, and nothing else. Okay, so fine. Now I'm going to substitute this part in the marginal PDFs here. So we can get fx of x is equal to the, so this quantity, it is written as a constant here. You can see this one. So fxy of x comma y into dy is there. So only the term related to y I'm going to keep inside the integral. The rest of the parts I'm going to take outside the integral here. I'm going to treat this as a constant here. This is the constant I'm going to treat here. Okay, so I'll take outside the integral the constant part here. So we are going to get e to the power of minus 0.51. So can anyone tell me what's the value of 0.51 divided by 1.02? 0.51 divided by 1.02. What's the value you'll get here?
0.5.
0.5. Okay, yeah, good. 0.5 x square divided by 1.4283 pi. Okay, so integral from minus infinity to plus infinity, e to the power of minus y minus 0.7x whole square divided by 1.02 into dy. Okay, so fx of x e to the power of minus 0.5 x square divided by 1.28305 integral e to the power of this one will get here. Okay, so right, fine. Now I need to convert this in the form of like this here, so that I can replace this entire quantity with the one I can do replace here. I can replace this to entire quantity in terms of this one. I can do replace here. Okay, so what shall we do now to consider this in terms of the u square by 2? Okay, u square by 2 if I want to consider here. So what shall I need to do is I'm going to substitute. Okay, I'm going to substitute this one because here we have 1.02 there. We want the root 2 we want here. So that's why I'm going to substitute this entire part is equal to the u. I am going to substitute here. This entire part is equal to the u by root 2. I'm going to consider here. Why? Because we want u square by 2 here. So here you can see the square is there, but here the square is not there here. So what shall I consider is I can make this one as the root I can make here, and I can extend the square for this entire quantity like this. I can extend now. Okay, so here we have 1.02 is there. Okay, the square is not there for the denominator here. Okay, so if I want to make this one as a square, I can substitute keep this one as a root. I can keep it here, and I can extend the square for the this entire quantity. I can do extend here. Okay, so I can substitute this is equal to the u here. But if I'm going to substitute this quantity is equal to u, I am not able to get 2 here. So that's why what I will do, I'm going to substitute this entire quantity is equal to the u by root 2. I'm going to substitute here. So we can convert into the form like this here. Okay, now we can convert this into the form like this. So we can apply this concept and we can reduce this one into the one we can reduce here. So this concept you are going to apply in the digital communication where you want to convert. We need to express the this exponential term. That is where we need to find out the probability of error. I told in the digital communication. Okay, so what happens here when you are going to transmit the symbol 1 or 0? Okay, so because of the transmission errors is nothing but because of the noise in the communication channel, it might be received as 0 1 1 1. It is going to receive here. So here we need to find out the probability of error. We need to find out here. So that one can be find out by integrating the. Okay, so this normalized Gaussian random variable. Okay, so from the location where 0 and 1 it is going to lie, from the location where 0 and 1 is going to lie, so we are going to integrate here. Okay, so we are going to get the exponential form, something like this you are going to get here. So at that time, since this integral it is difficult to evaluate, we are going to convert this part into the complementary error function you are going to convert here. So like in the Gaussian random variable, we have seen the table in the last of the textbook. I shared the table to you people. Okay, so like that we are going to convert in terms of a complementary error function. So there we are going to make use of this normalized Gaussian random variable concept. You are going to make use, and you are going to substitute that one in terms of express this one in terms of the complementary error function, and we are going to get the value of the probability of error we are going to get there here. Okay, so when you go to a sixth semester, you can able to understand this concept here. So now you remember the concept. I given the application where you are going to use, so that there we can apply this concept. You can apply there here. So right now what I am going to use. Let us substitute u by root 2. Why we need root 2 is because we need to express in terms of like this here. That's why I'm substituting as u by root 2 is equal to this entire quantity, that is y minus 0.7x divided by root of 1.02. Root of 1.02. Okay, we are going to substitute here. So now when I'm replacing with the term which is related to the dy, I need to find the value for the dy also. So in order to find out this one, what I'm going to do is let us differentiate both the sides here. Okay, so differentiate both the sides. So because we need to substitute for the dy also, so differentiate both the sides here. Differentiate both the sides. Okay, with respect to du here and with respect to dy here, already you know this basics of the mathematics. Okay, so here dy, because the x is the constant you are going to treat, so it will become equal to 1.02. We'll get a root of 1.02. Now we need to solve for the dy. Okay, so this implies that so dy is equal to the. Okay, so this is root of 1.02 divided by root of 2. Okay, into du. Dy is equal to root of 1.02 divided by root 2 into du. Okay, so let it be okay. So right, done. Now let us substitute dy here. Let us substitute dy here. Okay, so if you are going to substitute the dy here, so what we'll get is fx of x is equal to, so u by root 2 is equal to this entire quantity. When I take the square, it will become u square by 2 will become here. Okay, so e to the power of minus 0.5 x square divided by 1.4283 pi. So the limits will not affect here because it's infinity to the plus infinity to the minus infinity is there. So even any constant if you're going to add, it will remain same thing. So there is no need to worry for the limits of the integration. So it will become e to the power of minus. I'm going to keep this one as u by root 2. So in the next step, let us do evaluate here. So that will be not having any confusion. Okay, into dy. So dy is nothing but, so it is root of 1.02 divided by root 2 into du. Into du will get here. So right. Done. Okay, fine. Now I'm going to simplify this one. So I'll bring outside here. So it is e to the power of minus 0.5 x square into root of 1.02 divided by 1.4283 pi into root 2. So integral from minus infinity to the plus infinity e to the power of, when I apply the square here, it will become u square divided by 2 into du. U square divided by 2 into du. Okay. Done, right? Okay, so now I'm going to substitute, make use of this formula here. I'm going to make use of this formula and I'm going to evaluate this integral. I'm going to evaluate here. Okay, just a second. Yeah, so this formula is correct. So just I'm having the confusion whether it is 2 pi or root of 2 pi. It's a 2 pi only. Okay, now what I'm going to do is, if you consider this quantity, I think you can see now, 1 by 2 pi. Okay, so integral e to the power of minus u square by du. So here also integral is there, e to the power of minus u square by 2 into du is there. The quantity pi is also there here. Pi is also is there. So what you can do is you can multiply and divide by the 2 here. So you can multiply by 2 and divide by 2. So that 2 pi you can consider here. 2 pi you can consider. So fx of x will become equal to the, so e to the power of minus 0.5 x square. Okay, so into root of 1.02 into 2, so divided by 1.4283. So pi I am going to take here, so it is root 2. Okay, into 1 by 2 pi. So whatever the 2 we have multiplied, that's one I'm going to combine here. So minus infinity to plus infinity e to the power of minus u square by 2. Okay, into du. Okay, into du. Into du. Okay, so this quantity we know from the normalized Gaussian and available, so you can call this one as something called equation 1. You can call here. Okay, so you can call this one as equation 1. Okay, so I'm going to substitute from the equation 1. From equation 1, I'm going to replace this entire quantity with the 1 here. So in the meantime, let us simplify this one. So you can simplify and tell me the answer. 1 by root 2, root of 1 by 1.02 into 2 divided by this entire quantity. What will you get here? Can you get the answer for this one? Root of 1.02 divided by root 2 into 1.4283.
1.004.
Okay, so approximately you can take it as 1. You can take it. Okay.
Yes, sir.
Yeah, approximately you can take it as 1. You can take here. Okay. Then.
Yes, sir.
So done, everyone. Any doubts in this one?
No, sir.
What about others? So any doubts in this one? Understanding this concept?
Yes, sir.
Okay. Okay, so small confusion. Okay, so just I'm having the doubt here. Okay, small confusion. So this is root of 2 pi here. Sorry, root of 2 pi. That's why I'm having the small confusion. Okay, so root of 2 pi is this one here. So just that's what I'm thinking this one. So root of 2 pi is there. So here if you root of 2 pi is there, here it will become root of 2 pi will get here. So root 2 is there. Okay, so pi is there, no? So root 2 pi is there. So I think this quantity will become, so just you can make the small correction you can make here. So this is 1 by root of 2 pi here. Okay. So this time I'm in confusion. Just I check cross verify with the textbook here. So it is 1 by root of 2 pi. So make the correction. So if you are 2 is there. So I think no need to multiply with the 2 and 2 here. So this already root 2 is there and pi is there. In the pi you can take one root you can take here. So this has become root of 2 pi. This root 2 will be not there. So I think here it will become 1 point into root of 2 pi will get here. Root of 2 pi. Okay, so here it is 1 by root 2 pi. Okay, so make this correction, please. Okay, I'm having doubt with whether it is a 2 pi or root of 2 pi. Okay. So this problem we have seen in the exponential random variable. We have seen this concept. Okay, so this will
Sir,
become
in denominator it is 2 root pi, sir.
2 root pi. So here, what will happen now? 1.4283 is,
Final answer, sir.
root of 2 pi will get, I guess. Okay, so I'll explain the concept here. So here we have root of 1.02 divided by pi is there, and pi is there, right? Pi is there. Root 2 is also there here. Root 2 will come here. So this has become root 2 into pi 1.02 divided by this one here. So root of 1.02 is nothing but it is a 1 only almost will get here. So this one will become 1.414 will get, I guess. 1.414 is nothing but it is almost equal to the root 2. Correct now? It is equal to the root 2 will get here. So root 2 merge with root 2 pi. So it will become a root 2 pi here. So pi can be expressed as a root pi into root pi. So 1 root pi is here. So this one we can express as a divided by root of 2 pi into e to the power of minus 0.5 x square will get here. Okay, so just I will explain from this one here. So here we have substituted dy is equal to root of 1.02 divided by root 2 into du here. So that's what we have substituted here. I'm going to take this one outside the integral here, outside the integral. So this has become root of 102 divided by root 2. Here I'm not going to multiply any quantity here. Not going to multiply any quantity. Okay, so the remaining concept is this is the it is there here. So since I want 1 divided by root 2 pi, I want here 1 divided by root 2 pi. So already 1 pi is there. Okay, let us take root pi here. So the remaining quantity is root pi will be there. So 1 divided by root pi. Okay, so here 2 is not there. 1 divided by root 2 pi. Okay, so e to the power of minus 0.5 x square root of 1.02 divided by 1.4283. So root of 1.02 is almost equal to 1 point some change will get you 1.001 something like that here. Okay, so that one divided by this one, it will be results in the 1.414 almost it will get here. So this one can be written as root of 2 we can write here, and root of pi is there we can write like this here. So this will be this one will get. So where x can take the value minus infinity is less than x is less than the infinity it will take here. Okay, now got understood now?
Yes, sir.
Shall I redo from this part here? Shall I repeat from this part?
No, sir.
Okay, everyone understood, right? Everyone understood?
Yes, sir.
Okay, fine. I think everyone has understood. Okay, so I'm going to going forward. So we got fx of x is equal to these are marginal PDFs we got here. Okay, so similarly we can write for the other marginal PDF fi of a we can write here. So you can take similarly we can write the marginal PDF of phi of y is the thing, but I'm going to write the formula. So minus infinity plus infinity. So fxy of x comma y into dx we are going to integrate here. So if you are going to integrate, we'll get the same answer we are going to get here. That is 1 divided by root of 2 pi into e to the power of minus 0.5 y square we'll get here. So where y can take the value from minus infinity is less than y is less than the plus infinity it will take here. Minus infinity is less than the y is less than the plus infinity it will take here. Then
Yes, sir.
okay. Now in the previous problems we have seen. Okay, so what we have seen is once we find the marginal PDFs, we are going to verify. I think just I'm going to turn the page back here. Okay, so where we are done the verification. Yeah, so here we are done the verification here. So we got in the previous problem where we express the bivariate PDF in terms of the impulse function you expressed here. I told you how to express in terms of impulse function, how you are going to apply the time shifting property I told in this last class. Okay, so here we got the PDFs we got here, marginal PDFs we got fy of y. and marginal PDF fx of x we got here, where it is here. Yeah, so here it is there, somewhere it is there here. Okay, when I take the product of this one, the product of the marginal PDFs results in the bivariate PDF you're going to get here. Now let us cross verify that one here. Okay, so when I take the product of the two marginal PDFs, if it is equal to the bivariate PDFs, then we can say that the random variable x and y are said to be the independent random variables. We can say it here. Correct? No? Okay, so when the bivariate PDF is equal to the product of the individual marginal PDFs, we can say the random variables x and y are said to be independent random variables. We can say it here. Okay, so that one we did in the last class. Similarly, if the covariance is equal to 0, sorry, if the this one, what we said, if the expectation, that is, if the correlation, the expectation of x comma y, sorry, not correlation, it's covariance, right? Yeah. So when covariance is equal to the, it's this one, we can say when covariance is equal to 0, we can say that the random variables x and y are said to be uncorrelated. We find in the last class. Now let us verify. Let us verify this one here. The product of the marginal PDFs fy of y. Okay, marginal product of the marginal PDF fy of y and the fx of x. Okay, whether this one results in the bivariate PDF here. If both results here, we can say this bivariate PDF is it's a independent, the random variable x and y are said to be independent random variable here. So the concept what I'm telling you're getting right?
Yes, sir.
Okay, so just I'll repeat once again here what the concept here, so that there'll be no confusion. Okay, so what I said is we find the if, okay, we find already the marginal PDFs we find here, fx of x and fy of y we find here. If fx of x is equal into fy of y, so if this is equal to fxy of x comma y, fx of x comma y, then we can say, okay, then we can say the random variables. Okay, for the random variables, I'm going to use the short notation RV. Okay, x and y are independent random variables. We can say it here. Independent random variables. We can say it here. Correct? No, we can say this one is as the independent random variables. We can say it here. Okay, so that one let us verify now here. Here concept. Okay, so
Yes, sir.
when you take the product of this one, if it is results in the this bivariate PDF, we can say it's an independent random variables. If it is not equal, we can say the random variables are, it's not independent here. It depends on one another. It is dependent here. Okay, so we have fx of x. We have 1 divided by root of 2 pi into e to the power of minus 0.5 x square is there. Okay, into fy of y, we have 1 divided by root of 2 pi into e to the power of minus 0.5 into y square. So this, if I take the product here, when you take the product of this one, it will become 1 by 2 pi. So e to the power of minus, okay, x plus y, x square plus y square divided by 2 will get here. 0.5 is nothing but 2. Okay, so since this is not equal to fxy of x comma y, okay, so this one is not equal to x comma y. So we can say that the random variables x and y are not independent here. Are not independent random variables. Are not independent random variables. Okay. So like this, we can verify the properties here. So the properties are very simple here, but what we should do is one of the best practice in any programming, any problematic subject is, okay. So the best practice is at the end of the notebook. So before some 2, 3, 4 pages back, you make a list of the formulas here. Okay, they make a list of the formulas. Which are the formulas I'm going to tell important? You can make a list of the formulas so that whenever you get the problem, just turn the pages back and do the problem, so that you'll get you can remember the concept here and you can do the problem easily. You can do it here. Okay, so better you practice for this one, for the signal subject, control systems, for engineering statistics, which are the mathematics. Also, you can do this one. Make a list of the formulas, so it will be helpful for you when you're going to take the GATE exam. For example, if you're taking the GATE exam, at that time also it will be helpful for you people here. Okay, that's a better practice. You can do it. So if you want to remember the formulas, that's the best idea. You can do it here. I think you're done already in your PUC, all those things. So now also you can repeat that one, because what you are going to study the things, so that will be carry out for in your workplace also. It will be carry out there. So okay, so done. Okay, so now by making use of this concept, so this is an example of the one of the Gaussian distributed random variable where we got this one here. by making use of this concept, I'm going to extend the I'm going to define the normalized Gaussian random variable I'm going to define here. Okay, so I'll make use of this concept here, and I'm going to define the normalized Gaussian random variable for the two random variables. So already we have seen that one for the single random variable. I'm going to define this one for the two random variables I'm going to define here. Okay, so what we are doing in the module 2 is just extension of the module 1, that's it here. Okay, so in the module 1, what are the concepts we have seen? We have seen the this one PDF we have seen the cumulative distribution function we have seen the mean we have seen here. Okay, so mean variance sigma v square sigma x square. Okay, and we have seen the exponential random variable we have seen here. Exponential random variable we have seen the normalized Gaussian random variable we have seen here. So those concepts I'm going to extend for the fxy of x comma y. Okay, I'm adding one more random variable. Okay, so I'm going to add another random variable. So this is a bachelor. I'm going to make the marriage of this one, so that we'll get the bivariate or the two random variables you're going to get here. So this is two random variables I'm going to add. So this one I'm going to call it as the covariance you're going to call here. Okay, so for the single random variable, single Gaussian random variable, I'm going to find out the normalized Gaussian random variable for the two random variables we are going to consider. So here single was there, here it is married one is there here. That's it here. I'm doing nothing else I'm doing here. So this is before marriage, this is after marriage. That's it. Okay, now so when you are making here, okay, so there'll be a bit difficulty will be there here. That difficulty you need to extend, give some space for this one, give some space for this one, so that you're going to get, we can correlate the things easily. You can do it here. So right now, let us take the next topic. Take the next topic. The next topic is okay. So Gaussian bivariate random variable. Gaussian bivariate random variables. Gaussian bivariate random variables. So you have seen the Gaussian random variable for the single random variable we have seen here. That is, we are going to consider the normalized Gaussian random variable. I'm going to recall the topic, and I'm going to extend that for the multiple random variables you're going to extend here. Okay, so done. So you can take the normalized Gaussian random variable. The normalized Gaussian random variable. The normalized Gaussian random variable. So normalize nothing but we are going to normalize the Gaussian PDF. Okay, so the Gaussian normalized random variable. Gaussian random variable. The normalized Gaussian random variable X having the PDF and CDF. Having the PDF is nothing but the probability density function, and the CDF are given below. Okay, so already we did this in the module 1 here. So the PDF we can give, so it is nothing but, so in terms of the Z I'm going to consider here, fz of z is equal to, so it is 1 divided by root of 2 pi, 1 divided by root of 2 pi into e to the power of minus z square divided by 2, e to the power minus z square divided by 2, and the CDF of this one is given by fz of z is equal to, so 1 divided by root of 2 pi into e to the power of, okay, so that is we can, if you are going to integrate this one, you are going to get that one. So how to integrate is, it is integral from the minus infinity to the, so some variable called z here. So when you are integrating, we need to change the variables here with respect to tu. You are going to do integrate here. Okay, so this one we are integrating here. Okay, this is the CDF of the Gaussian random variable. This is the PDF of the Gaussian random variable here. So that we already see in the module 1 here. Now what you're going to do in this, under this topic is, I'm going to extend this single random variable into the multiple random variables. I'm going to extend here multiple random variables. Okay, so at that time I'm going to add the two random variables here. So that is become fx comma y. I'm going to add here. So it is something called okay, x comma y. In terms of z1, z2. So here z1 comma z2 I'm going to add here. Here also I'm going to make